So the first week, we worked on formalizing the mathematics of, you know how fast something is changing at every moment. You want to know how much you have at every moment. And how much you have of something, its amount, we said we built a net accumulation function. Like things reach an amount by growing bit by bit. And that's what we mean by net accumulation. They get to their current amount by growing bit by bit. And so that's our idea of a net accumulation function, given that we had the rate of change function. So then we looked at the first example or application of that, and that was accumulating area. And we saw that just the integral itself, did it give us area? Just the integral itself didn't give us area, but gave us what? Signed area, right? Like it goes down whenever the function's below the axis. All right, and so then we worked on that for a couple days. And so now we're on to volume. So let's just talk through the game plan for volume. What is it going to be like for volume? So what is it like to using integration to calculate volume? What does that mean? That means we're going to start with a curve, and we're going to rotate that curve or extend that curve. So in recitation, you'll have something different than rotation. You'll like be extending the curve, but you'll form a shell out of a curve somehow. You'll form a shell out of a curve. Usually that will be rotating the curve. And then we're going to fill the shell with right cylinders. We started working on those cylinders last time. We're going to fill the shell with right cylinders, and then we're going to track the amount of volume filled as we go. So this is exactly in line with what we're talking about. This forms a volume net accumulation function, right? The net accumulation of the volume of those shells, or cylinders, as they're filling up the shell. So this is the crux of it right here. We're going to fill up an empty shell with right cylinders. We're going to track how much volume we've accumulated in those cylinders as we go and as we fill up the shell. So what is that? What do we need to know if we want to come up with a volume net accumulation function? What's the key thing that we need to know? We need the rate of change of volume. You know how fast something is changing at every moment. You want to know how much of it you have. So if we had the volume rate of change function, we have our template, we have our general form for net accumulation, we're home free. That's it. All we need is the rate of change, and we can write our either net accumulation or total accumulation with our integral forms, right? The ones that we built up in the first week. So that means we need to know the rate of change of volume of the elements we are using. Okay, so that's what we started to do last time. We were looking at these cylinders, and we're looking at the height changing, and the whole goal there was what's the rate of change of volume of a growing cylinder. Okay, so let's just quickly go back and review. If you pull your sheet out, look at the first page, and let's revert back to area. So we get in this mindset of finding rate of change, right? So let's just so this side. Go to this side, page 1, and I want you to complete what we didn't, the first half of page 1. And you're asked to write what something. Whenever you're asked to write what something means, that means precisely and thoroughly, right? Precisely with all the details. So take just a couple minutes here. See how you do on the top, those two exercises there on the top half of that page right there. I have just a couple more extra. Hopefully most of you brought yours from last time. Behind you, please. Okay, Logan, where's Logan? Where's Logan? You are up, sir. What'd you say? The rectangle area grows at a, what'd you say? It was just working a second ago here. What'd you say? rate of, what's that? 4, rate of change of 4. Okay, good start. And then what'd you say for the, what is the meaning of that rate of change being 4? Okay, pretty close. Yeah, pretty close. So for any given change in x, so it grows at a rate of change of, and anything specific about that rate of change? Yeah, we could even say a constant rate of change of 4, which means that, so he said given any change in x, he said you're going to multiply that by 4, and then here was the part that we got to just clarify a little bit. If you multiply that change by 4, what do you get? You said area. You don't get area, you get...
4x.
No, but, okay, but so given any change in x, if you multiply that change by 4, he said you get area. Is that right? No, instead we get how much it increases, how much area increases, the change in area. So it was almost right. So given a change in x, the change in area, or the increase in area, is 4 times that change in x. And what's our, we could say, in other words, i.e., or in other words, what's our mathematical statement? Yeah.
dA equals 4dx.
Good. dA equals 4 dx. So no matter how much we increase by, the amount that the area increases by is going to be 4 times what we chose for our increase in x. So that's our constant rate of change. Okay? Then the next one. Any questions on that? Okay, so next one here is this one. The region's area grows at, what's that? You didn't get to this, okay? Anybody?
Varying rate.
What's that?
A varying rate of change.
He said a varying rate of change. Agree with that?
Yep.
Yep, now this is a good varying rate of change. Excellent.
Of
Of y. So is y right? Yeah, it's like the y value, and we also, that's also called f of x. But yeah, that's y. That's true. So it's a very rate of change, which means that what? What does that mean? Sophia, what did you say?
So at any given dx, dA increases by factor of x.
Given any change in x dx, you said the area changes by?
A factor of x.
So I just summarized. Is that what you said essentially? What I wrote? Is it given any change in x dx, the area changes by f of x dx? Okay, is that right? Something's not quite right about this. So yeah, we got the theme down, right? Given any change in x, the change in your dependent variable, in this case area, is going to be the rate times the change in x. We got all that. But there's something about this that we've got to kind of revise or clarify. What's that? Yeah, so that's kind of implied by the fact that we have f of x, yeah? So, what were we going to say? Yeah. Yeah, so there is a problem given any change in x dx. What's the problem with that? So let's say here we are at whatever this x value is. I want to pick my change to be this much. There's my dx, okay? For this x. How much area am I going to get if I multiply dx times f of x? Is it going to be right?
No, it's not
Too big or too small? do you see that if I multiply f of x by dx, I'm only going to get this much area. It's going to be too small. Why? Because as soon as I moved away from x, what happened to the rate? It changed. F of x was shooting up, and I was staying at f of x, the x that I started at. You see that? So what do I need? How do I need to qualify this statement? The statement's still true, yeah. Right. So this is only going to work now. If the rate is changing, your dx has to be really small, and then we can consider it essentially to be constant. So that's the big change here. Given any small change in x, that dx has to be small. Because if it's not small, the rate changes, but we're staying at that constant rate that was the first rate that we had at x. And we're not going to get the right area. But if we got a small change in x, then we can assume that our rate is essentially constant over that small change in x, and we'll get an accurate rate of change and an accurate change in area. Does that make sense why we need to make it has to be small when the rate is varying?
Is there like a certain interval that would qualify as small? Because I feel like just saying small would be very subjective.
Yes.
Like that could be considered small.
Right.
So it's kind of
Well, this is definitely, in this situation, this is not small, because you can see it's not even close. So that's not small. So not small is easy to determine, but then small would be, like you'd have, in a given situation, you'd have to say, it's kind of like what we did in that first week when we were looking at the different approximations. And then we finally got to where the accumulation function, it didn't really change anymore when we kept going smaller. So that in that situation, we were small enough. So it is, you're right, it's very subjective. But not small is easy to find. Does that make sense? Yeah. Okay, other questions? Okay, so we're talking about the rate. So that in this case, the rate of change is f of x. As long as we have small changes in x, we can get small changes in area by going f of x times dx. All right, so let's relate the rate of change to this situation. So where is this region, this gray region, where is it growing? Where is it getting bigger? It's growing up, right? Is that right? Is that how this region is getting bigger? Is it growing up like this? No. How is it getting bigger? Where? On the right side, right? Here's like the face or the leading edge where things are changing, right? Is that showing up as orange up there? Right there. That's where things are changing. And what did we say the rate of change was? F of x. How does f of x relate to that like leading edge or that leading face? How does f of x relate to that? How does the value of f of x relate to that leading face where the area is growing? The value of f of x. How does it relate to that right there? What's that?
is it the height?
Yeah, it is. It like is f of x, right? Like that height right there, that orange height that I drew, which is the leading edge of our region, that is the rate of change. That's f of x. It's like the height of the, and by leading edge, I mean like where the area is actually growing. It's like the face, the leading face, where it's actually growing. So the height of that thing, or the size of that leading edge, that leading face, is the rate of change. How much more area would you get if x changed a little bit? You get that much area, the height. That's how much more area you'd get. Down over here, if x was over here, you'd only get this much more height, this much more area for a change in x. So this is going to be really important. Wherever your entity is changing, however it's changing, the magnitude of that leading edge or that leading face becomes the rate of change. Does that make sense what I'm saying? So we're going to see this with volume too, okay? All right, so let's switch to volume. We were working on cylinders. Any questions on that? And we said those cylinders can increase in two ways, right? So we're going to use these kinds of cylinders where you see the green and yellow. And we're investigating the first way that a cylinder can increase, and that was in its height, right? So simply the height is increasing. And so we were investigating here what would happen if we changed the height. So we got the volume of a cylinder with a hole in it. So it's outer cylinder, solid cylinder minus the hole. And then we said, okay, what would the change in volume be if we increase the height by 0.4? So let's step back and say, why are we doing this? Why are we doing this? Because if I want to know the rate of change of volume with respect to height, what mathematical statement is going to kind of embody this idea of the rate of change of volume with respect to height? What mathematical statement would that be? Rate of change. Now I want rate of change of volume with respect to height. So what mathematical statement would we be after if we're talking about rate of change of volume with respect to height? Rate of change of volume with respect to height. Thank you. dV equals mdh. Wouldn't it be? That would be my rate of change of volume with respect to height. Just like dy equals mdx. Okay? So, what we're after is, we're after the rate of change of one of these cylinders as it grows in height. So this is what we're after the m. So the reason I'm posing this question of what is dV equal to is we want to make this, what we were doing here, look like this. And if we can make it look like this, then we'll know what the rate of change is. M. Does it make sense? So, what did we say? We said the change in volume for a change of 0.4. We could do final minus initial. So this was the final after the height was raised minus the initial volume. But then, at the very end, someone brought up very wisely. So here's this. So say here's this change in. Okay, so suppose that is the change. That's the new volume after the height was changed by 0.4. So that amount of change in the height, that red cylinder that I'm growing, do you see that it's just the exact same thing? It's really the same thing as the cylinder we started with. Do you see that? That amount of change when the height grew by 0.4 is really the exact same shape as the one we started with, but with a height of 0.4 rather than a height of 0.7 or 7. Do you see that? So another way, besides doing final volume by minus initial volume, another way we could do that is we could just say, let's just start over and just do the amount of volume with a height of 0.4. And so that would be like this. Now we're really close to dV equals mdh. What do we need? All we need to do is what? Because this is our dH, right? All we need to do to get it to look like dV equals mdh is what? I got a dH here minus something with a dH here. Yeah? I'm trying to make it look like mdh. So it's just one step away. What do? Just factor out dH, right? I'm just going to take a dH from both of these, but I'm gonna, instead of factoring it out to the left, like you normally do, I'm going to factor it on the right. I'm just going to pull a dH out, and what am I left with? Pi times v squared minus pi times 2.5 squared. And do I have something of the form dV equals mdh? So what is the rate of change? What's the rate of change of volume for changing height in these cylinders? So this is my m. M equals pi times, what does 3 represent in general? Outer radius, right? Outer radius squared minus pi times inner radius squared is my rate of change of volume with respect to height. Okay, but looking at that formula, Do you notice anything about that formula? What does that formula find? What does that formula find? Relative to our original cylinder, do you see what that formula is finding? What area? The area of the base, right? The gold, like the area of that gold ring. Okay, and what is that like? Where is the cylinder growing? On the right? Is it growing out to the right? Is it growing down? Where's it growing? Up. What did we say? Wherever this thing is growing, the rate of change is the size of the leading edge, the magnitude of the leading edge. What's the leading edge here now? It's not a length anymore, but a area, that gold area. That's what it is, right? So it's the same thing again. The rate of change is the size, in this case area, of the leading edge of how this thing is growing. Just like with the area example. Except in the area example, that was a length, that was a height where it was growing. Well, now this volume is growing. This leading edge is an area, so that area is the rate of change. So here's the big first takeaway. When your cylinders are growing by height, the rate of change is the area of the base. When your cylinders are growing in height, the rate of change is the area of the base. Okay, any questions on that? So now we said the other way that these cylinders can grow is in radius. That's the second half down here. So we're going to find, you're going to write a change in volume formula. Okay, we're going to write a change in volume formula for the radius. Let's just go right to dr. Okay, so let's not do 0.1. Let's just go right to dr. So if you have your cylinder and the radius changes by dr, then what will dV be? What will the change in volume be for a change in radius of dr? Okay, so I gave you I wrote this again there for the volume of the original cylinder. So I'm going to keep taking attendance, and so your job is, and then when we do this, what are we going for now? For this rate of change, we're going to go for what? dV equals mdr now. So now we're looking for the rate of change with respect to radius changing. So you're going to write your dV formula and then see if you can rearrange it to make it look like this. If you can, then you've got the rate right there. Just like the rate was the area of the base for this one. Okay, either making progress or you're getting help. You got 2 TAs, you got people around you. No sitting idly. Everyone's working. Go. Okay, so I've got it all here in this slide. I might go faster than you can write, so just listen and then go back to the video to get the notes, okay? So I might just listen and make sure you're following. So I started with this. Is that what you got for dV? So here's the original volume. And then the new volume is going to be the only thing, the outer radius grows by dr, but the inner radius stays the same. Do you follow that? Okay, so then we just have to do the algebra here. What are we after? We're after dV equals mdr. So we want to get something times dr. So the first thing you notice is that you've got, when you start working on this, you notice that this is minus this term. And then minus and minus is plus, and it's the exact same term, so those go away. Do you see that? So this is the opposite, and this ends up being plus, so those go away, first of all. And then you're left with this. Now, when you multiply this out, you've got a binomial squared. Notice that the first term, pi times 3 squared times 7, well, that's this. So the first term, so this is going to be 3 terms because it's a binomial square. The first term of it is going to subtract, this is going to subtract away, so that thing's going to go away. And we're just going to have the remaining, I'll just cross the 3 out, but it's really the pi times 3 squared times 7. So we're going to have the remaining 2 terms, the middle term and then the dr squared term. So that looks like this. Agree with that? So now what I'm going to do is, so we know we want dv times something dr, so like last time, we're going to factor the dr out. Factor the dr out. And actually I can factor out pi and 7 as well. So I'm going to factor out pi, I'm going to factor out 7, I'm going to factor out dr, and I have this. So then what's going to happen to dr? Dr is going to become small. So when it's multiplied, we want to keep it. Right? That's we know. That's dy equals mdx. Even though x is super small, it's still whatever change times the rate. But when we're adding and dr becomes small, what can we do? That can go away when it's added. When it's multiplied, we can't make it go away because then we just get 0. It's all gone. Right? But this is fair to say when dr gets small, that thing goes away. And so then we have this. So this goes to 0, right? That goes to 0. It's so small that we can ignore it in an addition, okay? So we got it. dv equals, what's our m? 2 pi rh. M is, this is equal to the rate of change of volume with respect to radius. What do you notice? Does it follow this pattern that we've been talking about today? What is that, 2 pi rh? Where does the 2 come from? The middle term. 2 times 3. So when you have a binomial square, a plus b squared, it's a squared plus 2ab plus b squared. Blast from the past. A squared, right? A squared. A squared plus 2ab plus there's where your 2 comes. It's the middle term when you FOIL. When you do outer, inner, and you add them together, you get 2 of them. Yeah?
So then 2 pi rh is just the surface area of the...
Okay, listen.
Yeah.
Yeah.
So it's the surface area of the cylinder if you take out this area of the circular faces.
Right. So how is this thing growing? Where is its leading edge? Used to be the vertical lateral area of this thing. And what is that vertical lateral area? So what I'm shading in red here, that area equals what?
2 pi rh.
2 pi rh. It's the circumference times the height. Circumference times the height gives that lateral area. And lo and behold, that's the leading edge of how this thing is growing, and that's the rate of change when the radius is growing. Do you see it? It's the same thing every time. Wherever your element is growing, that leading edge, the magnitude of it is your rate of change. Yes, sir. Yes, ma'am. Sorry. Yes, 3 is the outer radius. But now, yeah. But so now, yeah, but the dr is so small, so dr is going to be essentially going to be like this thickness right there. So it's so small that it's like just radius now. Yeah. Yeah, so they're essentially, I mean, when dr gets really small, they're essentially the same. So yeah, going with the outer radius. So 2.5 is essentially the same as 3. Okay, so now we're ready for an example. So we said when we rotate these curves to get these shells, we're going to fill them with these cylinders, and there's 2 ways the cylinder could be growing. It could be growing in height, or it can be growing in radius, and now we know the rate of change in both cases. Right? We know the rate of change when the cylinder grows in height. We know the rate of change when the cylinder grows in radius. So we got it. Now we can write these volume accumulation functions. So let's see what that looks like. Any questions on that? Okay. So here we're going to do sine, the function sine x. I showed you this before, from 0 to pi. That's sine x from 0 to pi. I'm going to revolve this around the x-axis to create an empty shell. Okay, do it again. So I'm revolving it around the x-axis to create an empty shell. And then what I'm going to do. So now I'm going to decide, my intervals, right? So I'm going to chop this up into intervals. Either I'm going to use, let x vary through delta x intervals, or I'm going to let y vary through delta y intervals. So I'm going to let x vary through delta x intervals to form cylinders that fill the shell. So let x vary through delta x intervals. And so what does that look like? So here's that empty shell. So what will it look like when x varies through delta x intervals to fill the shell? This is what that will look like. So here are my cylinders filling up the shell, accumulating volume, right? Accumulating volume in the empty shell. So now the question is, are these cylinders growing in height or in radius? Are these cylinders growing in height or in radius? In the current interval. Here's the key. In the current interval. In the current interval, are the cylinders growing in height or radius? In the current interval. So I'll pause it. The current interval is specifically the cylinder that has the pink band around it. That's the current interval. We're in a partially filled up now. So looking at just that current interval, just that cylinder in the current interval, is it growing in height in the current interval, or is it growing in radius? It's growing to the right. It's going this way. Would you agree? Is that the height or the radius? That's the height. It's just lying on its side, so it's not up and down height. But the height, it's the height. It's like, so it's the height of the cylinder, because this radius is up and down now. The radius is this way, so this is growing in height. All right, so I have a series of questions for you. That off the screen. No, that's later. This. Okay, so number one doesn't have to do with this particular problem. It's any problem. Okay, so number one is not for this one. Numbers 2 through 4 are for this one. But number one is for any problem. For any empty shell being filled, what function would give the total accumulation of volume starting from x equals 0? Write a general form. So that question is not specific to this. It could be any shell with any cylinders. Okay? Then 2 through 4 have to do with this situation. Okay? Problem. For any volume problem, what's our total accumulation function for any volume problem? Who thinks I got it? We worked hard on this for the whole first week of class. For any volume problem, what's the total accumulation? Someone, please. Yes. V of x, volume function, equals v of 0 plus integral 0 to x. Close. What dt? Yeah, really close. Rate of change of volume with respect to x, but using t. Remember that? We said that with any quantity, anything that's accumulating, any amount of stuff, all we need is its rate of change, and then this is its total accumulation function, and then specifically if we're starting accumulating from 0. Tom, do you have a question?
Yeah, why are we using t instead of like t?
That was our generic variable to use. Remember that? We always use the t in there. Yeah.
Doesn't the rate get squared, or am I getting ahead of myself?
Nope. This is our general total accumulation function. Works for any quantity: area, volume, temperature, distance, anything with force, work, anything that mass, anything that we want to accumulate. All we need is the rate of change of that quantity, and we can write down the total accumulation.
Okay.
So that was this thing this was our whole journey the first week of class, was to come up with that. Okay, now this particular problem, what do we need to apply the general form? So now we want to apply this general form to this. What do we need? Rate of change of volume. And what did we say? These are growing by how?
Height.
These are growing by height. Therefore, rate of change was? What was the rate of change? Area of the base. When the cylinders are growing by height, the leading edge is the area of the base. And so that rate of change is the area of the base. And so what is that?
I times R sub V of t.
No. What's the area of the base? Can I pause it? Pi r squared, right? I can't pause it from this screen here. It's going to be pi r squared. Of that black, see that the grayish, the dark black faces are pi r squared. Okay? What is r, though? So what variable are we using? Are we letting x increase through delta x intervals, or are we letting y increase through delta y intervals? So our independent variable is x, therefore we need the radius in terms of x. So we have our cylinder like this. The radius is this right here, and this is our curve, sine x. So what is the radius of our, it's the y-coordinate. Do you see that? The radius is the y-coordinate of the curve. So in this case, the radius is the y-coordinate, pi y squared, and what is y in terms of x? Okay, which is sine x. Yes, so f of x, yep, we could write pi f of x squared, and we could write pi sine x squared. Those are all equivalent. So for these particular shells, the radius cylinders, the radius of these cylinders is the distance from the x-axis up to the curve. That's the y-coordinate. And the y-coordinate is sine x. All right, so total volume, here we go. So Vx equals, for this one, V of 0. What is V of 0, by the way? How much total volume have we accumulated before 0? 0. So in this case, it's just 0, okay? From 0 to x of the rate of change of volume, which is our pi times sine of x squared. Would I need a? I don't want x there. I want t dt. Got it. So that's our volume accumulation, the accumulation of the volume of those cylinders as it fills up the shell.